All right, so the second part of your lesson today is imaginary numbers. It's going to be pretty straightforward. We've already kind of talked about this just because of the ACT. So part 63 is just trying to get you to the idea of, hey, by the way, when we do solve quadratic equations, there will be two solutions. So solving x squared equals 2, I would have to square root both sides. So the square root of x squared and the square root of 2 would give me x equals and then positive or negative 2, square root of 2. We have to remember that there's going to be two solutions to every single one of these problems. So that's what they're just getting at in 63. Now, there are two different historical notes just kind of explaining the whole background story of imaginary numbers and how they came to be, as well as irrational numbers and how they came to be. I think it's really interesting just to kind of know that backstory and where that all is coming from. So that's why that's in there. If you're looking at 64 and you can't see any numbers in there, just go on to the textbook and see if you can find them. For some reason, my copy is not showing up numbers right now. When we move on to 64, they're asking you to simplify these. So I'm going to show you these answers because I do think that these ones, as kind of a basis of where we're going today, are more helpful if you can see the answers. So the square root of negative 4, what they're trying to get you to do here is the idea that I can rewrite this as 4 times negative 1. And since we know, based on what we're seeing here, the square root of negative 1 is I can rewrite this as 4i squared, which would be 2i as my solution. In part B and C, they're just trying to get you the idea that we treat I like we would anything else. So this would become 6i squared, and since we know I squared is negative 1, I can rewrite this as negative 6. So I just multiplied together the 2 and the 3, the I and the I. That's how I got there. Part C, I would get 4i squared times 5i, which would give me 20i squared times I. Now you could write that as I to the third, but I'm leaving it separate because I notice I squared is negative 1, so I can turn this part into a negative 1 and get negative 20i. And part D, you don't have to show all of this work just to get to the answer. If you can do it quickly in your head, that's totally fine. I'm just showing you how they're getting there. So in part D, where they have the square root of negative 25, I could just immediately jump to 5i, and that's totally fine. When you move on to 66 through 69, they're really just talking about what this does on the graph. So ideally, what you're going to notice when you graph the function x squared minus 4x plus 5 is it may or may not cross the x-axis. And if it doesn't, what we're talking about is that's how we see these imaginary solutions show up on a graph, is they don't actually look like a solution because they don't cross the x-axis. That's where these complex numbers come into play. So part B, where they give us the quadratic formula and they ask us to use that to solve for our equation. So just a reminder, negative b plus or minus the square root of b squared minus 4ac over 2a. By the way, you cannot factor a quadratic equation that doesn't have real solutions. It won't work. That's why the quadratic formula becomes so important all of a sudden. So we would plug this in here. We would get negative 4 plus or minus the square root of negative 4. Remember those parentheses, squared, minus 4 times 1 times 5 over 2 times 1. So I always simplify these by using this part first, which is called the discriminant. So I'm going to simplify the stuff in the square root first before I try and type this into my calculator. So negative 4 squared is 16 minus 4 times 1 times 5, which is 20. So I get positive 4 because negative, plus or minus the square root of 16 minus 20, which is negative 4 over 2. Then I notice, hey, I have an imaginary number, which we just learned about. So the square root of negative 4 is 2i, so this could be written as 4 plus or minus 2i over 2, which actually simplifies because all three pieces are divisible by 2. So this can become 2 plus or minus I. This is what we call a complex number. So really the difference between a complex and an imaginary number is this part is imaginary, this part is real. So we call it complex because it has both pieces, where just this would be the imaginary, just this would be a real number. So that's the only difference there. You will more than likely see me write my answers like this when I'm dealing with a quadratic formula and then I have to write my two solutions as complex numbers, but technically this does represent two solutions. So a lot of times I'm going to ask you to write this out as two different solutions, so like 2 plus I, 2 minus I, in order to show that we have two different answers here. So as you move on to 67 and 68, they are again just asking you to graph and notice the way that this looks on a graph and how that works. again, the whole point is that imaginary solutions don't show up on a graph the same way that regular solutions or x-intercepts would. Eventually, we'll talk about what those look like on a graph.